Hello and welcome everyone to the third episode of Empowering 10x Engineers webinar series focused on RISC-V. I'm your host today, Bilal, co-founder of 10x Engineers, but I'm not the important person today. We have two speakers joining us, Basit Mahmood and Fatma Salim. So I guess it's time and let's get started. So Fatma, do you want to share the screen and let's get us rolling?
Yes, sure. Do you see my screen?
Can you see my screen?
Yeah, sure.
All good. So today, once again, welcome everyone. We're going to be talking about verification of RISC-V MMUs. Fatma and Basit are going to tell us about address translation and how it works in RISC-V. So if that's your cup of tea, you're at the right cafe. Fatma is a senior design engineer at 10x Engineers. She's been working on RISC-V for about 4 years now. The first project she worked on was verification of U74 class of course from Sci-5. Since then, she's been working on multiple RISC-V projects, including contributing to the open source CVA6 core and some of the client projects that involve RISC-V vector accelerators and other extension for other hardware. Welcome, Fatma.
Thank you.
Basit is an associate verification engineer at Impare. He was a key contributor to verification of the debug modules in the Open Titan project. That's a very interesting project going on in RISC-V. So really glad to have you, Basit. He has been working hands-on in RISC-V, so looking forward to hearing from you more about RISC-V verification.
Thank you.
So, quick intro of the two companies. 10x Engineers specializes in RISC-V design and verification and image signal processors. So those are the two areas we focus on. We have a RISC-V emulation platform. So if you want to run your CI/CD on RISC-V machines, we have a platform called Cloud5, and we have an open source image processor called Infinite ISP. Go to 10xengineers.ai to get more information about that. Impare is a center of excellence when it comes to ASIC verification, especially focusing on RISC-V. That's why we're here together. Impare's team goes through extensive training, and I know how hard Faisal has worked with that team. Their excellence is second to none, and they offer a great cost advantage. So if you're interested, please reach out to Impare for work on RISC-V design verification. With that said, once again, audience, thank you very much for joining us. We will take questions from the audience at the end of this session. But now it's over to you, Fatma and Basit. Take it away, please.
Yes, thank you, Bilal. Okay, our today's agenda is very interesting. So we'll talk about the MMUs and how the memory address translation process work in RISC-V, and what is the key component of the while verifying the MMU, and we'll take an case study of CV6 as well. So let's get started with the introduction of the MMU. Basically, memory management unit is a key component of which translate the virtual address to a physical address. So when there is a virtual memory enabled in a system, so while CPU do any access, load, store, or fetch, instruction fetch, it's going to produce a virtual address. So virtual address, but we know that DRAM is instantiated with the physical addresses. So MMU will take that physical address and look up with the page tables and produce a final physical address, which is going to point to the some location in the memory. Okay. Also, let's now start with the like how the RISC-V defines the MMU spec, and let's start with the privilege modes. RISC-V gives us the three major privilege mode: user, supervisor, and machine. Machine mode has the highest privileges, and also while the supervisor mode has less. So and user mode. User mode and supervisor mode could be normal and also virtualized when there is a hypervisor extension enabled. So there is a different combination available for different modes. When we have simple M mode, there is no protection layer, and when we add the user mode with the machine mode, we'll add with the protection. So and there is a third combination of machine, supervisor, and user. So supervisor, when we there is OS layer, we need to enable the virtual memory. So we add up the supervisor mode. And the fourth one is when there are multiple OSs running, and hypervisor will manage all the OSs, and hypervisor will talk to the hypervisor execution environment. And then at the end of it, there is a hardware, and the application layer will talk to the different layers depending on which combination we are using. So for and as we see, let's try to focus on this part: machine, supervisor, and user mode. So user mode we'll add the spot for the virtual memory in the RISC-V, and RISC-V defines different levels of the page tables, and for 32-bit machine or 64-bit machine. For 32-bit, we have SP32, which traverse to the two levels of page table to get a physical address from the virtual address, and there are two levels of page table for RB32, and the standard size for the page table is 4 KB, and there is a 2:10 page table entry for SP32, and for RV64, we have different options depending on the which virtual address width. So if we have a virtual address of 39 bits, we will use the SC39 scheme, and it's going to have the three level of page table, and the smallest size is 4 KB still, and for SP 48 and SC57, the level keep increasing, and we have also different combinations of page table sizes. We will see how we get 1 gig to mega page tables. So for 64-bit combination, the page table entries is 512 to raise to power 9. Okay. So I've been talking about the page table entries. So what is the page table entry? For example, the MMU will take this input. This is the virtual address, for example. I'm taking the example of RVST32 and simple three levels of translation for RSC39. So For SU32, we have 32-bit virtual address. We produce for 34-bit physical address, right? And when there is SU39, 64-bit, we have 39-bit virtual address, and we'll produce 56-bit physical address. And but using the page table. So what is a typical page table entry look like for the lower bits? 32 bits are similar for 64 every mode. SE39, SE32. So we'll start with the valid bit, which will indicate like this page table entry is valid. And we have a combination of different permission bits, which is read, write, execute. So typically we use, as I mentioned earlier, like we will going to use access the memory in three purpose. Like we are loading it. If loading a memory data from the memory location, we will need that read permission of that memory. So basically these bits are protecting that memory region, basically. And if we are storing to the memory location, we need the write permission. And if we are fetching from that memory location, means like the instruction fetch in the fetch stage of the pipeline, so we will need that execute permission. And this user bit is basically if the user mode is accessing that page table entry, so we'll need to give the permission to the user mode for this page table entry. And also we know that in a single CPU there could be multiple processes will be running. So sometimes we will need to separate out the memories for each process. We want that process 0 couldn't access the process 1 memory, so we will define that accesses to for different processes separately. But and that work has been done using the ACID field. Like there are address space identifiers we assigned to identifiers for each memory location, each process different identifier. And but when we we want to like give all address spaces all permissions the same permission, so we'll set this global bit high. And there are two more bits, access and dirty. So when these bits are managed by the hardware. So if it means that this page has been accessed, and dirty means that this page has been written. So and some reserved bits, and we have the real physical address on the upper bits. And SE39 add up more bits to the physical PPN, and there are more reserved bits. So now let's talk about the actual process of translation, like the major steps. And we have talked about the page tables and entries. Now let's walk through the process of translating the virtual address. So we need to start from somewhere, right? So the SATP CSR to provide us with the base address of the first level. So we take that CSR and use its PPN and multiply it to the page size. So for example, we have this page, we saw that page table 1 KB, and we will multiply it to 12 bits. So, and we'll take that VPN 0, VPN 2 from the virtual address and index through this page table and find our first PTE. So there we talked about these permission bits, and the combinations of each bit defines a specific purpose. Like if read is 1, we can read to the page. Write is 1, we can write to the page. But when all permission are 0, that's not a reserved. It means that this PD is pointing to the next page table base. So we'll take if MMU will check these bits. If it all zeros, then it will take this PTE and use this PPN and multiply it to the page size and find the next page table base. So, and also for this level 1, we will take VPN 1 and index to the next PT, and we will repeat the process, right? We'll check the bits. We will check the bits and and also if all zeros, it means that's not a leaf PTE. It is pointing to the next page table entry. So we'll take that PPN and left shift it to the 12 bits, and then also at this level we'll take VPN 0 and find the final PTE, and the PTE should be valid and with the right combination of these bits. If any of the checks fails, we'll get the page fault. Okay. Now the interesting part is we can stop at any level, right? For example, if we check that PT, these bits weren't 0, and there were a legal combination of these bits, and PT was valid. So that means we have the final leaf PT at this level 2. So that means we have 1 giga page, right? Because we stopped at to restore 30 bits. So and we'll only take at this PT, we will only take the translation of the VPN2. We'll just copy everything else from the virtual address to the physical address. And if we stop, this could also happen at this level 1. So at this level, if we find the leaf PT, we'll have the 2 mega page. So and also the page so the larger page, RISC-V use the terminology of super pages for these type of pages, and super pages must be aligned to the specific, so 1 giga page should be aligned to the 1 gig boundary, otherwise you'll get to have a page fault. So on the top of it, like basically the virtual memory adds a protection, right? We are protecting the memory region. Is it normally it is a 1K 4K pages size of memory. We can also set the read, write, execute permission bits, and we also have the execute only pages. Like you can only execute from these pages, right? This is only for memory reserved. Instructions reserved. So the combination, obviously, if we can write to the page, we should be able to read it, right? If we are not able to read it, the combination is reserved. Like we don't use it, right? By default, the supervisor mode cannot access the user page. So if we are supervisor need to access the user pages, so there is a some bit in the status register to, and we'll set this bit high, then we can access the user pages. So there is a protection between the modes as well. And similarly, the S mode cannot read execute only pages. So if there are execute only pages, like there are some instruction sequence that user mode was running, so and we get the trap, but S mode needs to know that which instruction was that trapped. So we need to read that page. So we need the read permission supervisor. Then there is another bit, MXR bit, to override this permission. So when we set this make executable readable bit high, then a supervisor mode can read that page. So, and also supervisor mode can be enable, disable virtual memory, and choose the page table depth in the SATP register. The SATP register was CSR that we start from. And on the top of all these permission setting of the page at the page level, there is also a feature of physical memory protection unit, which can also add the protection layer next to this. So because for example, using this page level, we can only protect one whole page. We cannot protect within the page. We cannot change the accesses between like in between the single page. So PMP provide us that like granularity to like protect even I think up to 8 byte page as well. So we're not going to, because this is a separate topic, so the physical memory provide this protection. Okay, now let's take a look at some MMU implementation case study of the CVS6. CVS6 is an open hardware core. Now I'll hand over to Basit. Basit would talk about more about the MMU implementation in CVS6. Thank you.
Thank you, Fatma. And welcome to the fascinating case study of the CVS6 a noteworthy member of open hardware core family of open source RISC-V cores. So let's dive into the key features and characteristics that make the CVS6 stand out among its peers. So CVS6 is the part of the Open Hardware Core 5 family, representing a commitment to open source hardware and the RISC-V architecture. So it operates with a 6-stage in-order single-issue execution pipeline, making it efficient for a wide range of applications. The CVS6 supports both RV64GC and RV32GC instruction set architectures, providing flexibility to address different system requirements. This adaptability ensures that the cores can cater to a basically variety of applications. So with support for bit manipulation extensions, the CVS6 enhances its capabilities in processing and manipulating data at the bit level. This is crucial for tasks such as cryptography, data compression, and other bitwise operations. So CVS6 goes a step further by supporting Zcon and ZCB, contributing to its versatility in handling the complex instructions and enhancing its compatibility with a diverse set of applications. Designed as a flexible Linux-capable application class cores, the CVS6 is well suited for a variety of applications ranging from embedded systems to more complex computing environments. A standout feature is the ability to generate 32-bit or 64-bit RTL code from the same source code. This allows the developers to tailor the code to the specific requirements of their target systems. For enhanced security, the CVS6 implements the PMP physical memory protections, which safeguarding both data and instruction accesses. This ensures a secure and controlled environment for sensitive information. The CVS6 takes a significant stride in memory management with its level 2 shared TLB, specifically designed for SV32 based instructions and data address translations. So this contributes to the efficient virtual to physical address mapping. So that was a brief introduction of CVS6 core. Now let's move to the point that how MMU is implemented in the CVS6 core. So the MMUs SV32 manages privilege levels and access control, enforcing permissions for user and supervisor modes while handling access exceptions. It basically employs TL-based translation look-aside buffers for efficient address translation, reducing the needs for page table access. So TLB hits yield quick translations, but on misses, the shared TLB is consulted. And if necessary, the page table walker performs page table walks, updating the TLB and managing exceptions during the process. In addition to these functionalities, the MMU SV32 seamlessly integrates support for physical memory protection, enabling it to enforce access permissions and memory protection configurations as specified by the PMP settings. So this additional layer of security and control enhance the management of memory accesses. The MMU SV32 maintains interfaces with the instruction cache and the load store unit. It receives virtual addresses from these components and proceeds to translate them into physical addresses, which is a fundamental task for ensuring program execution and memory accesses. So that was the point that how the MMU is implemented in CVS6 core. So now let's come to the verification of CVS6 MMU. So now Fatma will tell that how the verification is done in the CVS6 MMU.
Thank you, Basit. So for the verification purpose of CV6 MMU, 10x actually there is an effort going on in the open source community of the open hardware to verify this CV6 core to and make it ready for ASIC ready for TRL level 5. So and for this effort, different open hardware member, including Thales, Open Hardware, and etc., and also 10x, is making effort to verifying this core. So for 10x will take the took the responsibility to verify the MMU, and we started off with the SV32 implementation of the CV6, and first step is to verifying its it at a architecture level. So for the architectural testing, we know that we used the verification environment of also the open hardware's verification environment of CoreVerif, which is a co-simulation environment which used Spike as a Bolton reference model. So we started out with developing the comprehensive test plan, and with that comprehensive test plan for the SV32, we wrote self-checking test, assembly test for each like test cases in the test plan, and at the end we run that in the co-simulation environment, and check if the result was fine. So and the test categories of different test categories measure for this test plan was checking the SATP accesses, in examining the various common cases related to in all the modes, and there is a PMP permission, because the PMP checks also perform on the PTE level as well, because reading and writing the PTE itself. So and the PT validity and permission that bits we talked about, like the PT is valid, or and read write execute permissions, and combination of it. So the reserve bits and all that. So and we also check the access of the supervisor and user pages. We saw that like there is a different permission settings between the supervisor mode accessing the user page level. So we saw that are we by enabling those settings we get the proper permission, and also if we don't have the permission, we'll get the page fault. And these are the executable page readability, the same for the MXR bit, and using the also the sum bit we talked about, like making supervisor mode accessing the user mode. And there is also access and dirty bit implementation, how these are implemented, because these two bits are handled by the hardware itself. And also there is a misaligned super page. So super page concept, we already talked about how we create the page super pages, and if we have unaligned super pages, I'll get the trap. So we checked about that as well. And also if if someone is interested in like taking a look how the whole process of verifying the CV6 is coming through, so we recently did this talk on the YouTube of Open Hardware TV channel, where we explained how different members are verifying and documenting and enhancing the design features of CV6 processor. So there is a detailed talk on it, so please go and check this out. Also, on RISC-V recently ratified the spec for the IOMMU as well. So what is an IOMMU? Basically, as we have a MMU for the CPU, which is translating the virtual address to the physical address, and basically there are devices, peripheral devices. I'll take the example of PCI. So if there is a PCI device is connected to a system, so we will, and the CPU is configuring that device, so CPU will going to use the virtual addresses to configure that device. So when the device is going to access the system memory, it will going to do that by using the virtual addresses, and IMM will take that address and produce the physical addresses to complete that access. So this spec has been ratified, and there are major. So it does connect the IO subsystem to the system memory. So there is a two address translation and protection. Basically, the two stage address translation will come in play when we have a hypervisor as well. So and also if there is a PCI address translation services and page request services also like enabled using the IOMMU. So, and there's a separate spec for advanced interrupt architecture as well. So using the MSI virtualization, we can have that interrupt routing through the IOMMU to the CPU. So, and there is a hardware performance monitor as well, which is monitoring the performance of the IOMMU as well. And it can also support the concurrent devices as well. Like I've seen, like in this diagram, we can see there is a one device A, which is actually the attached to the multiple other devices. But there is also could be some other device, like there is a device B in parallel of, which could be PCI or any other. So, and that will also use this IOMMU to go through this bus and access the system memory. I think that's a very interesting IP. So, okay. Yeah, I think that's it from my side as well. Thank you for joining. And I think back to you, Bilal.
Thank you, Fatma and Basit. That was quick and that was information rich. I'm sure there are a bunch of questions. I already see one from Homero. Will the slides be posted somewhere? That's a good question, Homero. Can you post a message under the LinkedIn page where we had this so we can share the link with you? I don't exactly know if we're planning to post the slides. The video will be definitely up, so you can replay this. But I'll make sure I get you the slides. So thank you. Thanks for the question. So Fatma and Basit, I had a couple of questions. So I'll start with Basit. Basit, CVS6 code base, does it only support SV32 or other modes are also supported? Because in one of the slides, it mentioned SV32 as an example of what's supported, but does it support SV39, etc.?
Basically, CV6 has two configurations, CV32A6 and CV64A6. So CV32A6 supports SV32 and the CV64A6 supports SV39 as well. So SV32 and SV39 is supported as well in the CV6.
I see, but not SV48, for example.
Yes.
And Fatma, you mentioned sort of this open source project where we are verifying the MMU for CVS6. Is that project completed? Is that still in progress? Can you give us sort of an update on where things stand and when will this be ready for somebody to use in their product?
Yes, actually, that's a very interesting question, because that's a complete effort. Like having we have back in a year, I think, a year before, we defined the different stages of this project, the step 1, step 2, and step 3. Step 1 is verifying the initial architecture verification of all the extensions, all the features, and step 2 is the micro architecture verification. So I'll say that step 1 is completed, and we are in step 2, and step 3 is like getting the 100 on all the coverage numbers. So we are into step 2. So we are we are focused on 32-bit configuration for now. So hopefully by the end of Q4 24, I will have the all these 3 steps completed, and we will have the verified 32-bit version of CV6.
Got it. Thank you. And I assume if people are more interested, they can join Open Hardware or join one of the meetings.
Yes.
Where the status is discussed, because it's an open source project, so anybody can.
Yes, anyone is more welcome to join this effort, because there is a lot to do in this open source community, and very interesting peers and colleagues whom we can learn and work together. So, yeah.
Excellent. Yeah. The more the merrier. That's the mantra for every open source project. All right. Which physical address sizes are supported is Akib's question. Basit, do you want to take that? Is there any limit for, say, RV32 on the support on the size of the physical addresses, and then you can go on for RV64 and RV128?
Okay, I'll take that. For SV32, the physical address generated is 34. So for SV 64, we have different choices for using the ST39. Like when the virtual address is 39, we'll get the 56-bit physical address. And in more detail, you can also go through the spec for RISC-V that listed all the different page sizes and according to your choice. So I think the physical address is 56 bits for 64-bit. Yeah, RV64-bit. Yeah.
So Akib, Fatma is leaving you with some homework. Do the math in your head. 56-bit, how many addresses? What's the address space from there? But thank you, Fatma.
Thank you.
Yeah, the stuff is obviously specified in the spec. So I had a couple of other questions. I'll go ahead and ask. We have some time, so I'll go ahead and ask this. So Fatma, you talked about IOMMU at the very end. Is there an open source implementation of IOMMU as well, or is it still at a very early stage and we only have a spec? You mentioned that the spec was recently ratified.
In fact, this is a really right time to ask this question, because recently, I think Zero Day Lab open source there. It's basic implementation, design implementation of the IMMU. It's not comprehensively complete, but it's a bare minimum which could be hooked up to the. In fact, they used CV6 as their reference and hooked up their IMMU to see if it's work. But yeah, I'll just say, because spec has recently ratified, they used a spec and implemented the bare minimum functionality, but which is not verified yet. But it is there is a, I think, demo available online. So. And I think they also presented their IMMU back in RISC-V Summit, Barcelona. So, and now in this, I think 1 week ago, they open sourced it finally. Their first release.
Awesome. Very good. Thank you. Thank you. Alrighty, and Basil, one more question for you. You worked on CVS6. You obviously described to us sort of in some detail the architecture of it, the microarchitecture details. Is CVS6 something that teams, product teams can pick up and use in their commercial products? What do you think? What's your take on this?
Yes, CVS6 silicon proven core. So it has been used previously. CVS6 is used with the OpenPython to create many core CPUs, and including an instance that tape out by Intel on their FinFET process. So yeah, it is a commercial core. So any company can use it in their project.
And looking at it on the inside, do you recommend that people use it? I'm just joking.
Yeah,
okay,
for
so
sure.
There's one more question. Okay, there's one more question from Akib. What type of performance extensions are you planning for? So yeah, both of you, either one of you can take that. Okay. What kind of extensions are planned to be added to? I assume the question is about CVS6.
Yeah, CVS6. Actually,
what kind of extensions is the community plan?
Yes, because recently, and RISC-V is working on adding new extension spec as well for some purpose. Like for example, I'll take the bitmanip as example. For adding the bitmanip extension, we'll have the. I think Basit also explained the the benefits of that extension. So we added that extension to CVS6, which increases performance as well. So we planned new extension which could also increase the performance and also reduce the code size as well. So there is a new extension that recently had been rectified, that ZCB, which is used to reduce the code size. That implementation is in progress in the Open Hardware project. So 10x is doing it, and also there is a new extension ZIcon. And there are multiple in pipeline, so we'll just take and experiment a little bit about it, like how it will going to impact the overall project, and we're going to increase the performance. Then we'll finalize the project, and there's a whole process, the complete process in defining the project and getting it approved by the Open Hardware. So that's these are two still in the play, like adding the ZCP. I think.
All right, thank you, Fatma. So I just realized that Homero and I have actually met. Homero and I were housemates last year when we both were at the RISC-V Summit, and we ran into each other in the kitchen one day, and we started talking about RISC-V. So he's a student, and I'm sure there are other students logged in. So Basit, hi, Homero. Do you want to talk about how can students learn RISC-V if they are interested? What should be the starting point? Because I think for a lot of students, where to get started is the question, is the challenge.
Yes, for as a starting point, there is a course on EDX by David Harris and Sarah Harris, and there is a book, Digital Logic and the Computer Architecture. So that is a good reference for starting point. And there is a course of UC Berkeley CS 152. So that could be another good starting point for learning the RISC-V. So I will recommend these two courses to start with the RISC-V.
Sounds good. And like Homero, you can try to come to the RISC-V Summit. There are scholarships and available for students to join the summit, get to meet people who are working in this area and learn more. So thank you very much. Akib has a correction on his question or clarification. He said, my question was related to MMU like SVNAPOT and SVPPMT. Yeah. Okay. So Fatma, you want to take that?
Yes, sure. Actually, these two extension. For example, I'll take the if we are need to like edit the permission, give the permission to some specific. So these are two extensions which do not supported by CV6 right now, and these are reserved for future use. But spec for these two has been defined, and RISC-V ratified those. But these are basically the implementation dependent. If you really need that functionality, you can just go ahead and add this field in the PTE and implement that extension. So yeah, the CV6 doesn't support that right now. And I don't think so. There's a plan to add this in a near future as well. So yeah.
Oh, that's too bad. Well, if Akib, you want to add these to CVS6, more than welcome to join the community. Yes. So Sani is asking, what advice do you have for students? How can they learn about RISC-V and enter the semiconductor industry? So Basit answered. Fatima, you want to take a stab at it as well? Is there anything you advise the students to?
Actually, Basit has pointed to the content material, but interestingly, when you go to the RISC-V GitHub page, they also included the repository to learn. And when you go into that repository, you have all things at one place, the content and everything. And the RISC-V community is making a lot of effort to that project, like getting everything together for someone who wants to learn. So I think that's a very good spot to look at. I think so.
So I'll add my 2 cents to it. If there's a student listening and you're really interested in learning RISC-V, connect with the two of them on LinkedIn and badger them with all your questions.
Sure.
I'm sure they'll both be happy to help. Is there a plan for adding hypervisor support, Fatma,
yes.
to CVS6?
Actually, hypervisor support has already been added to CVS6, but it is not mainstream yet. It has been like tested, but not thoroughly. Like the verification we do. So that's a blocking point currently. So the design implementation is there. There is a separate branch for it. Like in fact, the 0-day labs like contributed the hypervisor extension to the CV6 as well. So it does for 2-stage translation with SV39 cross 4. So that's already done, and like it's just pending verification, thorough verification, but it's in the repository.
So Akib, now you absolutely have to join, I think, the CVS6 design and verification. Thank you very much, Fatma. So Fatma, I believe we're running out of time. So one final question that came from Ragad. What has been your experience like working in the engineering field? I know from past experiences that engineering companies, including those who work in sort of computing area, um, do not have very fair representation of girls. So what has been your experience
Yes.
working in this industry? Do you recommend for other girls to join?
Sure, of course, I do recommend because, in fact, in my experience from the past 4 years, I have seen the growth in the female community in this field, and there are more eager girls join doing the engineering and joining the industry because and I think for me personally, this has been great opportunity to we had the opportunity back in 2019, and we took that. We didn't know at the time that what this interesting industry will look like, but when we started out, and it was really amazing, and you get to learn and work with such an amazing people, and I think that's a really challenging and like pushing you further in this industry. You need to push, and I think that's a really good spot for girls. And also when someone say like if you wanna uh, do engineering or doctor, and everyone say like, oh girl, will need to go to the doctor field, but the engineering field is much more interesting than the doctor. So okay, I'll like surely suggest joining this field, and it is interesting and competitive. So
Thank you, Fatma. So fortunately, there were no doctors on the call, I think.
yeah, no, just
Thank you so much, both of you, and thank you, Para team, for helping organize these webinar series. It's great having all of you here. Thank you so much, and have a wonderful day, afternoon, night. See you next time in the next episode. Bye bye.
thank you.
Thank you so much.